So now it's time to determine the scattering states for the delta potential. The delta potential that we're using here is just minus alpha times the delta function of x. In the previous video, we solved this problem for the bound state, and now it's time to do it for the scattering states. Now remember, scattering states just means that the energy will be taken to be positive. So if we make this little sketch here, this will be x, and we take in this axis the potential. Then this potential will just be this infinite dip right here. Obviously this is not infinitely narrow as it's supposed to be because it's a delta function, but this is just here to give us an idea of what's going on. So in the previous case we had some wave down here, but now what we're going to have is going to be something going on over here. So we have to determine what exactly is going on, right? Because our energy is going to be greater than this potential. So that's why this is going to be a scattering state. It will not be bound by this potential as was the previous case. So let us now solve the Schrödinger equation. So let's just begin by writing it down as we have done many times. Dx squared plus the potential times the wave function equals to e psi, right? We're just leaving the x dependence out since it is just the same everywhere. So now we have to look at our two regions. We have region 1 here, region 2 here. So in both of those regions the potential will be 0. So we can actually solve them in a very similar fashion. I will only solve this for one because it's the same for the other case. So the potential is 0 in these regions psi 1 and psi 2. So what we get is squared psi dx squared. This is going to be minus 2me divided by h bar squared psi, right? We now have to solve this differential equation. That's what we're doing. We have done this many times before. So since the energy here is positive, we just define this as minus k squared psi with k equal to 2me divided by h bar squared. This is k squared, right? So k is just going to be the square root of this. So, and just in case you're maybe having some doubts here, how to know when we have to put a minus sign in here or not, that depends on this e, because if you take a square root of this, you need to have something that is real. So in this case, the energy is positive, so this is fine. But if the energy was negative, we would have to have taken all of this as our k, so that the minus outside cancels out the minus that's going to come from the energy, and what we have inside of the square root is something positive. So now we just get this very familiar form that I hope you have seen many times, and we did see it in this series. So if you're unsure how to solve it, just go back a few videos. I'm just going to do this quickly. We can factor this out, right? At least this is the technique that we are always using. Plus ik d over dx minus ik, and all this times psi. This is going to be equal to 0. So now we just solve this differential equation, and then we solve the same one but with the plus sign. So we get two possible solutions. So in the first region, we are just going to call them a e to the I kx, and then we have a second possibility, which is the minus sign, right? Both of these are solutions. Each one of those comes from one of these cases. So in order, that's why we have these two. And in the second region, since it's the same differential equation, we are going to have the same solution, but obviously we have to take different these constants because it's a different region. Okay, so these are our two solutions. It's very similar to what we have solved in the past, so that's why I didn't want to go too deep into that. So now let's just take a look at this, because this time what we're going to have is that this will be traveling waves, right? As we saw in the case of the free particle, this is the form of these traveling waves. So what does this mean about our problem? So, and that's also why this is called this problem, these scattering states, because as you can see here, we are going to have a particle traveling to the right. If you can't see it, I talked more about it in my video about the free particle case. So if you are not sure why, then you should probably take a look at that first. And that's also why we wanted to first look at the case of the free particle and then take a look at this. Okay, so this first part here is just a wave traveling to the right, and this here is going to be a wave traveling to the left. And in the second region, this is going to be traveling to the right, and this is going to be traveling to the left. So let us just draw it. We're going to have this a e to the I kx, right, going to the right. Then we have b e to the minus I kx going to the left. Then we have c e to the I kx going to the right, and d e to the minus I kx going to the left in this second region. So this is a scattering problem, and usually what we do in the scattering problem is basically we're going to be sending in some stream of particles, right? So there's going to be some incident wave. So it depends if we are going to be sending the particles from the left or from the right of this potential. If we are doing scattering from the left, then our incident beam of particles will be related, actually will be this part right here, this a to the e I kx. And if we're doing scattering from the right, then the incident beam will be this d part right here. And in the first case of scattering from the left, what is the meaning of all of these other quantities? Then b is just going to be the particles that reflect off of this potential. C will be those that transmit across this potential. But what does d mean? So if we are doing scattering from the left, d will not really have any meaning. So d should be 0. There's no reason for d to exist unless we are sending particles from both sides at the same time, which is not really the way we want to do experiment, because that just makes everything way too messy. And in the other case, if we're doing scattering from the right, it's literally the same thing, but in the other case. So in that case, a would be what would have to be 0, since that would be the one that doesn't really have any physical meaning anymore. So while we can't say that any of these has to go to 0, as we did in the previous case, because one of the terms blew up before, that doesn't happen anymore, but we know that either a or d have to be 0 depending on whether we are doing scattering from the left or from the right. And another thing to note is that these states are not going to be normalizable, and that is actually to be expected because this is a free particle state. This is a free particle basically. So the same logic applies here as what we saw in the case of the free particle in a few videos in the past. But just as before, there is a way to just take these solutions and use a linear combination of them to write the actual solutions. But that is very tough to do, and it's actually beyond the scope of what we usually want to see in this introductory course of quantum mechanics. So given all of that little talk, let's actually now determine or see what we can get to know about these coefficients, because in these scattering problems we want to know, well, what's going to happen, what is the probability, or how many of our particles are going to reflect back, how many will be transmitted. That's what we want to know. So we want to find out what b and c are, but since this is not normalizable, it's really not that easy to do in that sense. So we have to do something else, and what we have to do is actually just as we did in the previous case. We are going to have to do these boundary conditions. So there's two main boundary conditions that we have to use, just as you do in those normal problems with waves. So first, our wave function has to be continuous at this place, everywhere actually, but especially at this place of interest, which is going to be when x is 0. So our two wave functions have to be equal when x is equal to 0. So that means that a plus b has to be equal to c plus d. Right? I still haven't decided if this is going to be scattering from the left or from the right. I'm going to do that a little bit later. So then we have the second, this is condition number 1. Then we have the second condition that tells us that if this potential is finite, then the derivative should be smoothly continuous. But this is not a finite potential, so we have to take a look at what happens to this derivative. So we want to know what is going on with this. So just as we did in the previous video, we now have to ask ourselves, where can we get information about this? And well, if you saw the previous video, you can skip ahead a little bit. I'm just going to do it in case somebody didn't see it. And this is just going to be, well, where can we find this? This is something that appears in kind of in the Schrödinger equation, except in the Schrödinger equation, you have the second derivative. But if you integrate the second derivative, you get the first derivative. So one thing you could try is say, okay, so let us just integrate all of the Schrödinger equation across this region of interest. So it's going to be from some minus epsilon, which will be just very close. Let's say it's like here, and then we are going to take the limit when it goes to 0. So we take minus epsilon and epsilon. So that's going to be the range where we are integrating this. So basically we are only interested in the Schrödinger equation, but across this potential, right? So, and this is going to be minus h bar squared divided by 2m, second derivative with respect to x, dx. And then we have this term with the potential. So this is going to be integral from minus epsilon to epsilon, potential of x, psi of x, dx. And this has to be equal to the integral minus epsilon to epsilon, energy psi of x dx. But this term right here is going to be 0, as we have already explained, because this is going to be just something with a finite height and with a vanishing width. So it's going to go to 0 as epsilon goes to 0, the integral, right? And then we have this other term right here. What is our potential? Our potential is going to be minus alpha delta x and, well, times psi of x. So when we integrate this, remember, if you are taking the integral of this delta function, all that will survive there is just this value where the delta is not 0, which is in this case at 0. So this will just be minus alpha times psi of 0, which is actually the same that we got in the previous video, right? So now let us solve for this. This integral is just going to be the first derivative evaluated between minus epsilon and epsilon. And we can now just take this part to the right and we can multiply by this. So we just get, let's see, it's going to be 2m divided by h bar squared. Then there's this alpha psi of 0. And let me just make sure that everything is, we add this. And oh, there's a minus sign. That's what I want to check. So that goes there, it's positive. Then we multiply by a minus sign, it's negative. Okay. And what is this thing right here? Well, this is going to be this discontinuity. So that's going to be the first derivative evaluated at epsilon, but epsilon is part of the second region. So we have to take the second wave function minus, well, evaluated at x equals 0, minus the derivative of the first region, or at the wave function of the first region, evaluated at x equals 0. So this is our condition, which is identical to what we saw in the previous case. And now we have to just find all of these quantities. So obviously psi of 0 is going to be easy. We can take any region because they're both equal at that point. But we do have to take this derivative. So let's begin by this second region. So in the second region, our function is c e to the I k x. So now that we're actually going to begin working with this, we have to choose and say, do we want scattering from the left or from the right? The results will be identical, just with switched values for a and d. But the idea is the same. So let's just say we're going to be doing scattering from the left. Okay, so d will be 0. So the derivative of this the wave function for the second region will just be ik times c, basically ik times this function. So this will just be ik times c, and this is evaluated at x equals 0, so the exponential will just be 1. And then we have the derivative in this first region, which will just be here ik times what we have here, and with a minus sign separating. So we get ika minus ikb evaluated at x equals 0. That's why the exponentials vanish. So when we now take this this minus sign here and we subtract them, we can factor out the ik. So we get ik times c minus a plus b, and this has to be equal to minus 2m alpha h bar squared. And now we have to take this psi of 0 So let's just write it as A plus B. Okay, so now we are actually quite close. We can now just begin solving this. So we can divide by this k, just put it down here, and this quantity that is right here, we can call it beta, because it's going to be, we are going to have to be writing it down a lot, so it's really nice if we can just leave it outside, right? It's really nice if we don't have to be writing that. It's not that big, but it's still nice to not have to write it all the time. So this will then be just minus 2 beta times A plus B. So now remember, this is a scattering experiment. So usually A is going to be some quantity that is either known or it's something we can control. So we want to know B and C, because those are the quantities that relate to basically what happens to these this incident beam of particles. Are they reflected? Are they transmitted? So we want to find C in terms of A and B in terms of A. So let us begin by solving for C, since there's only one C here. So we get IC is going to be equal to, now I'm going to multiply this through, minus 2 beta A minus 2 beta B, and then I'm just going to take these two terms and put them to the right. So we get plus AI and then minus BI. So now I can just factor here, and we get A times I minus 2 beta plus B. Actually, well, there's minus and minus, so let's just write it as minus B, and then I get A plus 2 beta. So now we can just divide all of this by I to leave this C here alone. So when we do that, this I right here will just be 1, and this will be divided by I. But if we just multiply and divide by I, we can write it up here, and the minus sign will change to a plus sign. So this is going to be 1 plus 2 beta I. That's just so that it looks better, and I don't have to take this divided by I. And we can here, well, we have to divide as well. So this I will be 1, and here we do the exact same thing. So we get minus 2 beta I. Okay, so this is C. The problem is we don't really know B just yet, so we need to write it in terms of A. So we know that C is going to be equal to A plus B. So B is going to be equal to C minus A, right? This is, by the way, just the first condition, right? The continuity of the wave function. That's why C has to be equal to A plus B, so B has to be equal to C minus A. So if I plug that in here, I get that C is going to be A 1 plus 2 beta I minus, and this B will now be C minus A times 1 minus 2 beta I. So let me just multiply this. So I get minus out here. Then we have C minus 2C beta I. And then we have minus A and plus 2A beta I. And we have this minus sign out here. So let's just put it inside. So we get minus C plus this, minus that. And I'm going to erase this and just write it up here. And just to make sure this is a minus sign, I don't want to get confused later on. So now this right here, minus 2A beta I, will cancel out this 2A beta I. Then we have A here, so we're going to get 2A on this side. And then on the right, we have this minus C. We can just add it up, so we get 2C, and then we have this 2C beta I, so we can write it as minus 2C beta I. So we can actually divide all of this by 2 and factor by C here, and we will find that C is going to be equal to A times 1 divided by, it's 1 minus beta I, right? We factor 1 minus beta I, yes. Okay, so that's going to be C. That's going to be our coefficient of transmission, and we can actually find it if we know what our A is, right? If we know the amplitude of this incoming beam, or whether it's a wave or it's this beam of particles or whatever we're dealing with, as long as we know its amplitude, then we can determine C. Now, well, let me just take it to the next page. And now we want to determine B. So the easiest way is just to plug this into the first condition, right? A plus B is equal to C. So as we saw before, that means B is going to be C minus A. So let's plug this in there, and we get that B is going to be A divided by 1 minus beta I minus A. So here we can factor out the A's, take the common denominator, so we get A 1 minus 1 plus beta I, right? Because there's this minus sign here, so we get double minus sign. 1 minus beta I. We get 1 minus 1, this cancels out. So we get that B is going to be A times beta I divided by 1 minus beta I. Okay, so now we found C and B. I'm just going to write them in the next page side by side, because now we want to talk about them a little bit. So remember, B is going to be this amplitude of the reflected wave of particles, or the reflected particle, right? So that's what we got. But the problem is we still need this A. So, and we do like to work with probabilities here. So there is a way in which we can actually make this a whole lot easier. So remember, our psi squared is just this probability density, right? The probability of finding our particle in this particular state. So if we take this, for example, B squared, and we divide it by A squared, what does this mean? This means, what is the probability of finding our particle in state B, but normalized by this amount A? So, and when we do that, we're going to see that this A is going to cancel out. And that is very good, because this is going to be then a relative probability. So, and that is actually a lot easier to work with, and it's actually going to give us a lot of information. So this is going to tell us what is the probability, the relative probability, that these particles will reflect back of this potential. So we're going to call this R because of reflection. So let us determine this. So we just take this B right here, we take its square modulus. So this right here is just going to be beta squared, and here we have to take the complex conjugate first before multiplying. So this is going to be 1 plus beta squared. So that's going to be the coefficient of reflection. Then we have another concept similar to this, but now we want to find what is this probability, the relative probability, that the particle will just go through the barrier. So in the same way, we just divide by this A to normalize it so that it doesn't depend on the incident amplitude, and we are going to call it T because of transmission, right? It's transmitted, so we just call it T. And in the same way, we now take the square modulus of this, so we get 1 divided by 1 plus beta squared. Okay, so in principle, this is the answer, but this is in terms of beta squared. So let us now just go back a little bit and remember what was beta. Beta was, if I remember correctly, actually I don't think yeah, let me try. It's alpha times, okay, I'm gonna go check. My memory is not that good. Let me see, where was it? There we go. It's m alpha divided by h bar squared k. So m alpha divided by h bar squared k. So that is our beta. So we can now write this into these two coefficients. So I'm running out of space here, so I'm just going to go to the next page. So now what we want to do is we want to determine these R and T, but in terms of our energy. And in order to do that, we need to get rid of these betas in terms of these other constants. But k is also just this variable that we created, so we need to write down what it actually is. So k is just going to be the square root of 2me divided by h bar squared. So that means that beta is going to be, let's see, m alpha h bar squared times k, but k is going to be, now since we are dividing by it, I'm just going to flip this, so we get h bar divided by 2me, and this is going to be to the 1/2 power. So we can actually simplify this further, so we're going to get m divided by 2e, all of this to 1/2 power, times h bar alpha, and then there's this h bar squared here, so actually it's just going to be alpha divided by h bar. Alpha divided by h bar. Let me just make sure that I did this correctly. So we have m alpha h bar, and then we substitute this in. We're dividing, so it flips. So h bar, this cancels out this square. Then we have 2me, the square root of that. Okay, so, and now let's plug it into our coefficient. Let's begin with r. So here it's going to be easier if we just divide everything by beta squared. So we get 1 divided by 1. This one is going to be divided by beta squared plus 1, right? We just divided numerator and denominator by beta squared, just so I don't have to write it twice, okay? That's actually the only reason why I did that. So we get 1 divided by beta squared, which, and since beta is this squared, well, it will be this squared, and it's flipped. So what we will get is going to be 2e h bar squared divided by m alpha squared plus 1. Okay, so let us now see the same, but with the coefficient of transmission. So if we do that, we get 1 divided by 1 plus, and now beta squared is going to be same, m divided by 2e alpha squared h bar squared. So what does this tell us? We are going to see that the coefficient of reflection, right, is going to be smaller when the energy of our particle is smaller. And that makes sense because if the particle has more energy, it will be easier to get across the potential that is to which we are scattering. It's going to be more likely to transmit, which is actually what we see in the second case, right? Here, the higher the energy, the higher the probability of transmission. And you can actually check, by the way, either with these two forms or with these two, but the first ones are obviously easier, that r plus t have to be 1. The particle has to either transmit or reflect. It can't just disappear, right? So that is it for this problem, and I will see you in the next video. We still have to discuss the delta potential barrier, so I will see you then.